It is generally not the inspector's responsibility to enforce personal preferences that exceed the established code requirements. Their primary role is to ensure compliance with the applicable codes and standards. In this case, the inspector's decision to require the reduction of wire size from 10 gauge to 12 gauge was not based on any code violation. The National Electrical Code, or NEC, does not prohibit the use of larger wire sizes for branch circuits as long as the maximum allowable ampacity of the smaller wire is not exceeded. The inspector's concern about voltage drop is valid, but the inspector should have addressed this by ensuring proper circuit design and sizing, not by mandating a specific wire size. The NEC provides guidance on voltage drop calculations and requires compliance with certain voltage drop limits, but it does not require the use of oversized wires solely for voltage drop mitigation. While the inspector's intention to protect future homeowners from potential electrical hazards is commendable, this does not justify enforcing a requirement that is not mandated by code. It is the responsibility of the electrician and homeowner to ensure that the electrical system is properly designed, installed, and maintained. The inspector should have focused on ensuring code compliance and provided guidance on voltage drop mitigation through proper circuit design rather than imposing a personal preference that is not code-based. The friend should have calculated voltage drop and ensured proper circuit sizing, but ultimately, the inspector should not have failed the installation based on a non-code related issue. While it is prudent to consider potential voltage drop issues and future safety concerns, it is not the inspector's responsibility to enforce non-code related requirements or to prioritize personal preferences over code compliance. In this case, the inspector's decision was not supported by the NEC and should not have been enforced. Now let us delve into the details about the National Electrical Code and voltage drop. The National Electrical Code, or NEC, serves as a cornerstone for electrical safety in the United States. It provides a comprehensive set of standards and guidelines for electrical installations, ensuring the protection of people and property from electrical hazards. The NEC is not a law itself, but it is widely adopted by state and local jurisdictions, becoming the legal basis for electrical inspections and compliance. One of the key aspects covered by the NEC is the proper sizing of conductors for electrical circuits. The code specifies the minimum ampacity requirements for conductors based on the load they are intended to carry. Ampacity refers to the current carrying capacity of a conductor, which is determined by its material, size, and insulation type. The NEC provides tables that list the ampacity of various conductors under different conditions. When selecting conductors for a circuit, it is essential to ensure that their ampacity is sufficient to handle the anticipated load. Overload in conductors can lead to overheating, insulation damage, and even electrical fires. The NEC also addresses the issue of voltage drop in electrical circuits. Voltage drop refers to the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can negatively impact the performance of electrical equipment, causing them to operate inefficiently or even fail. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. Branch circuits are the circuits that supply power to individual outlets or equipment, while feeders are the circuits that supply power to branch circuits. To minimize voltage drop, it is often necessary to increase the size of conductors. Larger conductors have lower resistance, which reduces the voltage drop along their length. The NEC provides formulas and tables that can be used to calculate voltage drop and determine the appropriate conductor size. In addition to conductor sizing, the NEC also covers a wide range of other electrical safety topics, including grounding, overcurrent protection, wiring methods, and equipment installation. Grounding is the process of connecting electrical equipment to the earth, providing a path for fault current to flow back to the source. This helps to protect against electrical shock hazards and prevent equipment damage. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. These devices interrupt the flow of current when it exceeds a safe level, preventing overheating and potential fires. The NEC specifies the types and ratings of overcurrent protection devices that are required for different types of circuits. Wiring methods refer to the ways in which electrical conductors are installed and protected. The NEC specifies the types of wiring methods that are permitted in different locations and applications. Common wiring methods include conduit, cable, and surface raceway. The NEC also provides detailed requirements for the installation of electrical equipment such as receptacles, switches, and lighting fixtures. These requirements are designed to ensure that equipment is installed safely and in accordance with manufacturer's instructions. Compliance with the NEC is essential for ensuring electrical safety. Electrical inspectors play a crucial role in enforcing the NEC and ensuring that electrical installations meet the required standards. These inspectors review electrical plans, conduct on-site inspections, and issue permits to ensure that electrical work is performed safely and correctly. Now to talk more about voltage drop. Voltage drop is an important consideration in electrical circuit design. It refers to the reduction in voltage that occurs along the length of a conductor due to the conductor's impedance. Excessive voltage drop can lead to various problems, including reduced equipment performance, overheating, and even premature failure. Several factors contribute to voltage drop in electrical circuits. These include the conductor's resistance, length, current, power factor, and temperature. A conductor's resistance is a measure of how much it opposes the flow of electric current. The higher the resistance, the greater the voltage drop for a given current. The length of a conductor directly affects voltage drop. Longer conductors have higher resistance, resulting in greater voltage drop. The amount of current flowing through a conductor also affects voltage drop. Higher currents lead to greater voltage drop. The power factor of a circuit is a measure of how effectively electrical power is being used. Low power factors can increase voltage drop. Temperature can also affect voltage drop. As the temperature of a conductor increases, its resistance also increases, leading to greater voltage drop. To calculate voltage drop in an electrical circuit, several formulas can be used. These formulas take into account the factors mentioned above, such as conductor resistance, length, current, power factor, and temperature. One common formula for calculating voltage drop is voltage drop equals current times impedance. This formula is applicable to alternating current circuits. For direct current circuits, a simpler formula can be used: voltage drop equals current times resistance. Several methods can be used to minimize voltage drop in electrical circuits. These include increasing conductor size, reducing circuit length, using conductors with lower resistance, improving power factor, and reducing temperature. Increasing conductor size is one of the most effective ways to reduce voltage drop. Larger conductors have lower resistance, which reduces the voltage drop for a given current. Reducing circuit length can also significantly reduce voltage drop. Shorter conductors have lower resistance, resulting in less voltage drop. Using conductors with lower resistance, such as copper instead of aluminum, can also help to minimize voltage drop. Improving power factor can reduce voltage drop by making electrical power usage more efficient. Reducing temperature can also help to minimize voltage drop, as lower temperatures lead to lower conductor resistance. The NEC provides guidelines and recommendations for voltage drop in electrical circuits. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. These limits are intended to ensure that electrical equipment operates efficiently and reliably. The NEC also provides formulas and tables for calculating voltage drop, which can be used to determine the appropriate conductor size for a given circuit. Electrical inspectors play a crucial role in ensuring that voltage drop is within acceptable limits. Inspectors review electrical plans, conduct on-site inspections, and perform voltage drop calculations to verify compliance with the NEC. Now let's explore conductor sizing and ampacity. Conductor sizing and ampacity are fundamental concepts in electrical engineering that ensure the safe and efficient distribution of electrical power. Conductor sizing refers to the selection of the appropriate size of an electrical conductor for a specific application, while ampacity refers to the maximum amount of electrical current that a conductor can carry continuously without exceeding its temperature rating. Several factors influence conductor sizing, including the load current, voltage drop, ambient temperature, and installation conditions. The load current is the amount of current that the conductor is expected to carry under normal operating conditions. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to its resistance. Ambient temperature is the temperature of the surrounding environment, which can affect the conductor's temperature rating. Installation conditions, such as whether the conductor is installed in conduit or free air, can also affect its temperature rating. To determine the appropriate conductor size, engineers use tables and formulas provided in the NEC. These tables list the ampacity of various conductors based on their size, material, insulation type, and installation conditions. The NEC also provides formulas for calculating voltage drop, which can be used to determine the minimum conductor size required to meet voltage drop requirements. Ampacity is a critical parameter that must be considered when selecting conductors. Exceeding the ampacity of a conductor can lead to overheating, insulation damage, and even electrical fires. The ampacity of a conductor is determined by its material, size, and insulation type. Copper conductors generally have higher ampacities than aluminum conductors for the same size. Larger conductors have higher ampacities than smaller conductors. Different insulation types have different temperature ratings, which affect the ampacity of the conductor. The NEC provides tables that list the ampacity of various conductors based on their material, size, and insulation type. These tables also take into account the ambient temperature and installation conditions. Correction factors are used to adjust the ampacity of conductors for ambient temperatures that are higher than the temperature listed in the tables. Dating factors are used to adjust the ampacity of conductors when multiple conductors are installed in close proximity. Proper conductor sizing and ampacity are essential for ensuring the safe and efficient operation of electrical systems. Undersized conductors can overheat and cause fires, while oversized conductors can be unnecessarily expensive. By carefully considering the factors that influence conductor sizing and ampacity, engineers can select the appropriate conductors for each application, ensuring the reliable and safe distribution of electrical power. Electrical inspectors play a crucial role in verifying that conductors are properly sized and have adequate ampacity. Inspectors review electrical plans, conduct on-site inspections, and perform calculations to ensure compliance with the NEC. Now let us talk about the inspector's role. Electrical inspectors play a vital role in ensuring the safety and compliance of electrical installations. These professionals are responsible for enforcing electrical codes and standards, protecting people and property from electrical hazards. Electrical inspectors typically work for local or state government agencies. They review electrical plans, conduct on-site inspections, and issue permits to ensure that electrical work is performed safely and correctly. To become an electrical inspector, individuals typically need to have a strong background in electrical work. This may include completing an apprenticeship program, earning a degree in electrical engineering, or working as a licensed electrician. Electrical inspectors also need to have a thorough understanding of electrical codes and standards, such as the NEC. They must stay up to date on the latest changes and interpretations of these codes. The specific duties of an electrical inspector vary depending on the jurisdiction and the type of inspection being performed. However, some common duties include reviewing electrical plans to ensure that they comply with applicable codes and standards, conducting on-site inspections to verify that electrical work is performed according to the plans and codes, identifying electrical hazards and violations, issuing correction notices and orders, and investigating electrical accidents and incidents. Electrical inspectors have the authority to enforce electrical codes and standards. They can issue correction notices to require contractors to fix code violations. They can also issue stop work orders to halt electrical work that is being performed unsafely or without a permit. In some cases, electrical inspectors may also be involved in legal proceedings related to electrical code violations. Electrical inspectors play a crucial role in protecting public safety. By enforcing electrical codes and standards, they help to prevent electrical fires, shocks, and other hazards. They also help to ensure that electrical systems are installed and maintained properly, which can improve their efficiency and reliability. The electrical inspectors must exercise their authority responsibly and ethically. They must be fair and impartial in their inspections, and they must avoid conflicts of interest. They must also be knowledgeable and competent in their field, and they must stay up to date on the latest changes in electrical codes and standards. Now let's explore circuit design and safety. Circuit design and safety are paramount considerations in electrical engineering. A well-designed circuit ensures efficient and reliable operation of electrical devices, while safety measures protect users from potential hazards. Circuit design involves selecting appropriate components, arranging them in a functional configuration, and calculating circuit parameters to meet specific requirements. The design process begins with defining the circuit's purpose and specifications. This includes determining the input and output voltage levels, current requirements, frequency response, and other relevant parameters. Once the specifications are defined, engineers select appropriate components such as resistors, capacitors, inductors, transistors, and integrated circuits based on their characteristics and suitability for the application. The components are then arranged in a functional configuration to achieve the desired circuit behavior. This may involve using series, parallel, or series parallel connections, as well as feedback loops and other techniques. After the circuit configuration is determined, engineers calculate circuit parameters such as voltage, current, resistance, and impedance to ensure that the circuit meets the specifications. This may involve using circuit analysis techniques such as Ohm's law, Kirchhoff's laws, and Thevenin's theorem. Circuit safety is an essential aspect of electrical engineering. Electrical circuits compose significant hazards such as electric shock, fire, and explosion, if not designed and operated safely. To mitigate these risks, engineers incorporate safety measures into circuit designs. One of the most important safety measures is grounding. Grounding provides a low resistance path for fault current to flow back to the source, tripping circuit breakers or fuses and preventing electrical shock. Another important safety measure is overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, protect circuits from excessive current, which can cause overheating and fires. Insulation is another important safety measure. Insulation prevents current from flowing through unintended paths, reducing the risk of electric shock. Electrical enclosures protect circuits from environmental factors, such as moisture, dust, and physical damage. Electrical enclosures also prevent accidental contact with live components. Regular maintenance and inspection are essential for ensuring circuit safety. Electrical systems should be inspected periodically to identify potential hazards such as loose connections, damaged insulation, and overloaded circuits. Maintenance should be performed to correct any identified problems. Electrical safety codes and standards provide guidelines for designing, installing, and maintaining electrical systems safely. These codes and standards are developed by organizations such as the NEC and the Institute of Electrical and Electronics Engineers. Compliance with electrical safety codes and standards is essential for protecting people and property from electrical hazards. Now let's look into homeowner responsibilities. Homeowners have several responsibilities when it comes to electrical safety. These responsibilities include ensuring that electrical systems are properly installed and maintained, using electrical appliances and equipment safely, and being aware of potential electrical hazards. Homeowners should ensure that electrical systems are properly installed by hiring qualified electricians. Electrical work should always be performed by licensed and insured professionals who are familiar with local electrical codes. Homeowners should ensure that electrical systems are properly maintained by having them inspected periodically. Electrical inspections can identify potential hazards such as loose connections, damaged insulation, and overloaded circuits. Homeowners should use electrical appliances and equipment safely by following manufacturer's instructions. Overloading circuits, using damaged appliances, and tampering with electrical wiring can create safety hazards. Homeowners should be aware of potential electrical hazards such as frayed wires, overloaded outlets, and water near electrical equipment. These hazards should be addressed promptly to prevent accidents. Homeowners should never attempt to perform electrical work themselves unless they are qualified and experienced. Electrical work can be dangerous, and it is always best to leave it to the professionals. Homeowners should teach children about electrical safety. Children should be taught not to play with electrical outlets, cords, or appliances. They should also be taught to stay away from downed power lines. Homeowners should have a fire extinguisher readily available in case of an electrical fire. The fire extinguisher should be rated for electrical fires. Homeowners should know how to shut off the power to their home in case of an emergency. The main electrical panel should be easily accessible and clearly labeled. By following these electrical safety tips, homeowners can protect themselves and their families from electrical hazards.